Hello everyone, welcome back, and in this section we are going to see about the evolution of word vectors and sentence vectors. We have learnt about TFIDF, but at a broader context, let's even understand how TFIDF represents words, sentences and paragraphs. This is going to be a very interesting comparison that you need to keep in mind. If anyone talks about any algorithm about word vectors or sentence vectors, think about how that algorithm will represent a single word, a single sentence, and a collection of sentences, which is a document or a paragraph. So let's understand how TFIDF represents a word. So for example, if you just take the word Batman, you know that TFIDF will calculate the TFIDF value for the single word Batman. Essentially, a word is represented as a single value called the TFIDF score. And remember that this TFIDF value captures how frequent this word is in a given movie plot or document, and also how rare it is across all the documents or the corpus that we have. Although from any given document we can extract any word and calculate TFIDF score, you need to remember that at some level you cannot really compare TFIDF scores of different words and say that they are similar or dissimilar, because at the end of the day it's just capturing the corpus and document frequency and nothing to do with the relationships of different words with each other. So the thing to remember is that a word is represented by just a single value. And when it comes to sentence, let's take a sentence like Batman Begins is directed by Christopher Nolan. What happens is that again, this is going to be represented with a long vector, because we take the whole corpus and how many ever words that we have in the corpus, those are the columns or the features. So you can assume probably there are 60k features or 60k columns, and you realize that if you take Batman Begins directed Christopher Nolan by ignoring the stoppers, you almost have just 5 non-zero values in this long 60k length vector. So a sentence is represented by a very long vector which is mostly sparse, that is, it contains mostly zeros, only few values are non-zero. And just extending that to paragraph, what happens is similar again. You basically have a very long vector of 60k length or so, and then probably you have 200 unique non-zero values, etc. if the paragraph has, let's say, 200 unique words. So at the end of the day, a word is just a single value. A sentence is a very long vector that is mostly sparse, and paragraph is also a very long vector that is also mostly sparse. Now the thing to remember is that TFIDF can only help you on a high level. When you want to do something like similarity matching or long document classification, etc., then you can use this vector and compare against each other or do some classification tasks. So at the end of the day, TFIDF metric essentially captures word frequency and word rarity across documents, and whatever comparisons that you do among different TFIDF vectors, they are just matching similar words and frequencies with each other. And you can already see some of the shortcomings of TFIDF, because you can only do like similarity comparison or classification on a very high level at document level, because you are essentially comparing word frequencies and word overlaps. And you need to remember that there is no word level similarity. That means a word like school is just as far from Batman as it is from college. Essentially, school and college should be closer together in high dimensional space, and Batman should be farther. But in TFIDF case, school, Batman, college has just one single value, so you cannot really compare those values with each other. and TF-IDF values are very dependent on the corpus. And when you have short sentences, essentially you don't really have enough context to get good vector representations or doing comparisons with each other or classifications, because it's going to be a very sparse vector. And at the end of the day, all these shortcomings are significant in the sense that since you have very sparse vector, like for example you have 100k columns and only very few values are filled, you cannot do any strong comparisons or classifications, etc. You can see that our immediate goal is to move away from just word frequencies, but rather capture word distributional semantics. That means which words co-occur with each other and what words come in the similar context, etc. Because we want to be able to compare school with college and say that these two are closer together when compared to Batman. And the other thing is that we need to move away from this sparse vector representation and come to dense vector representations. For example, if a sentence could be represented in just 364 length vector or 768 length vector, that's perfect for us, because now you can do comparisons of sentences or documents or paragraphs with each other, and also in a high quality manner, because these are dense vectors, they will also capture similar words together, etc. So exactly taking the point of TF-IDF where a word is not represented by a vector and you do not know anything about how similar two words are together, etc. To overcome that, we have this word vector algorithm. Essentially, word vector algorithm or Word2vec as they primarily call it, what it does is to convert each word, for example king, man, queen, woman, etc. Each of the word is converted into a long vector of length, let's say 368 or 768, etc. And the important thing to remember is that the word vectors are trained on a corpus in such a way that the vectors actually capture associations among different kinds of words. That means at the end of the day, if you have vector of king, vector of man and vector of woman, just like how you can do real world comparisons, if you can just add king vector with woman vector and subtract man, you'll get another vector which is close to queen's vector. So at the end of the day, you can do quite a lot of comparisons, just like how real world mappings occur. You can do similar comparisons of word vectors. You can find the plural of a given word, or you can find the past tense of a given word, etc. And how are these word vectors trained? So just like you had movie corpus, you can take any large corpus, text corpus of data, for example from Wikipedia, and you can train your word vector algorithm on the whole corpus, and you can finally get the word embeddings. So what essentially happens is that you will take, let's say, single sentences, and within a sentence you will take some kind of sliding window. For example, for every given word you will take the left two words and right two words, and your goal is to predict the middle word when given the other keywords. So a neural network algorithm is trained to predict the focus word, that is the middle word or the prime word, given some surrounding words around the focus word. So let's make that clear. So for example, if you just have a sentence like Batman Begins is a 2005 superhero film directed by Christopher Nolan, what's going to happen is that you'll take a sliding window of, let's say, 5 words. Here, if you come to this, then you have this 5 word sliding window where film is in the middle. So what's going to happen is that in the input, you again have all the unique words in the whole corpus. Then assume that there is a neural network. You don't really need to understand what this neural network does at the moment. All you can assume is that it's kind of like a black box. So given the surrounding words for this sentence, for example, 2005, superhero, directed, and by, if you give those words as input to this neural network, it should be able to predict the missing word, which is film. So again, the output will have all the probable words in the corpus, maybe like 50,000 words or 100,000 words, etc. When I mean predict the word film, essentially each word in the corpus will be just associated with some token. So just you can think of it like a numbering scheme, and let's say this token represents, or this output represents the film word. All you're trying to do is adjust the weight of the neural network such that this output gets the highest score, which corresponds to the word film. So when I mean the input is words, again they are not simply words, they are just tokens or indexes. For example, 2005 could be some index and superhero could be some index, let's say 10th word or something like that. Just you give this whole corpus column here, on the output you have similar. So the neural network is trained such that you take this 5-word context, you give the input words, and you tune the neural network such that the output word is film. Essentially that particular output has the highest score among all the other. So there are several ways to train, where you can give the context words and try to predict the missing word or central word, or you can do the reverse as well. There are several ways to train word vector algorithms, but I'm just giving you a very simple example. So at the end of the day, what's going to happen is that you will take these 5-word contexts from the whole corpus. So if the corpus has, let's say, 100,000 movies or 10,000 movies, then you collect such sentences and you train the algorithm. For example, if you just give this context and ask a human to predict, what they'll do is they might predict movie or film, right? So similarly, when the word vector algorithm sees hundreds and thousands of these sentences, it will automatically identify that movie, film, cinema, all these words come closer together because the context, surrounding context is the same for all the words like film, movie, cinema, and it is going to generate vectors for film, movie, cinema such that those individual vectors are very close to each other. So at the end of the day, once this algorithm is trained, again food and related words are closer together, film and related words are closer together, or let's say you have Batman and related words, other superheroes, heroes like Spider-Man, etc. are closer together. And essentially what's going to happen is that for a given word, for example film, what we are going to do is after the whole training is done on the whole corpus, maybe like 100,000 or 500,000 such 5-word context, if we take and train, we are going to collect the weight vectors of the last layer of the neural network that connects to film. So maybe there are 768 outputs at the very end that connect to film, and after the whole training is done, what we simply do is for film we collect the 768 length vector, and that's the word vector. Similarly for food, there's a 768 weight vector that we collect, that's the word vector for it. And for the whole corpus, maybe like 50,000 or 100,000 words, for each of the word we have a vector representation of length, let's say 768, etc. And the most interesting thing is that unlike TF-IDF, we have trained word vector algorithm by taking the distributional semantics or the surrounding words around a given focus word. So just because we have the surrounding context preserved, we are able to put together similar words in a closer vector space because of this training strategy. So that's the key that you need to remember. Now coming back to our comparison of word versus sentence versus paragraph, what's going to happen is that any given word, for example, Batman, will have a single vector of 768 dimensions. So when I mean a single vector, it's just one long list of 768 numbers, and those values are just float values like this 0.1234, 0.768 and all these things. And what happens with a sentence is that again we take a sentence and divide it by words. For example, here we have 1, 2, 3, 4, 5 words if we take out is and by as stop words. And what we are going to get is that we are going to get 5 vectors of 768 dimensions. And how do you get the sentence vector? Essentially, you just average the vector of individual words in this sentence and you get the final averaged vector that is of 768 dimensions. And same goes with paragraph. So paragraph, you take all the words, for example, maybe 100 words, and for each of the word you get the word vector and you average across all those 100 word vectors and you get the final paragraph vector or document vector. So at the end of the day, remember that for TFIDF, there was no vector, there was just one single value. And for sentence in TFIDF, there was a sparse vector of very long length, and similarly for paragraph. But when it comes to Word2vec, unlike TFIDF, instead of a single value, we have a single vector that is of 768 dimensions or whatever dimensions you trained for. And in sentence, you have dense vector instead of a sparse vector. So instead of 50,000 dimensions, etc., you have a dense vector that is of 768 dimensions or 360 dimensions, etc. And similarly for paragraph, you have a dense vector as well, which is of fixed dimensions. Now the interesting thing to remember is that still with word vectors, we have some issues. TFIDF had some issues. We tried to solve some of them and we made a better representation with Word2vec. But still Word2vec also has some shortcomings that we need to overcome. So the first thing is there is no word sense disambiguation. What I mean by that is if you take a word like mouse, that could mean a computer mouse or it could mean the house animal mouse. The thing is that there's only one entry in the lookup table of Word2vec. So it does not hold two different embeddings for these two different senses or contextual meanings. So at the end of the day, if your corpus has both computer mouse and the house mouse, then the word vector for the mouse will be confused and it's kind of like an average between these two contexts. So it will not really capture the context correctly. So the short thing to remember is that since there is no word sense disambiguation, for words that have multiple meanings, still we are going to have just one single vector, and that might not be ideal for most of the use cases because we need to have vectors that are contextual for a given word. And the other thing to remember is that if you are trying to get sentence vector, what we are trying to do is we are just averaging the word vectors of individual words in the sentence to get a sentence vector. But that doesn't really suffice because sometimes you need smart weighted averaging because some words are more prominent or important than the other words. So you need to give weightage to the sentence vector such that those words and their corresponding word vectors have a higher score, higher weight factor when you're averaging, but that's not preserved when you're trying to take sentence vector. And the other thing to remember is that if you just take plain Word2vec algorithm, if a certain keyword is not there in the dictionary lookup, that is the vocabulary created after Word2vec algorithm, then that word is completely ignored. What I mean by that is, let's say if you have a sentence like Ramsri is going to college, then going college will have word vectors in the vocabulary of Word2vec, but Ramsri, the word will not be present. So when we take the average sentence vector, we are going to completely ignore Ramsri because it is considered as out of vocabulary word. After Word2vec came out, which is one of the first algorithm to do this word to vector conversion using neural networks, there are several variants that came out, and one of the variant was called as fast text by Facebook. And fast text, what it does is that a given word, if there is no direct entry available in the vocabulary to get the word vector, it is going to split that word into sub words. So essentially a word like Ramsri could be divided into RAM and Sri, which might individually have entries in the word vector algorithm. So our sentence Ramsri is going to college will now be Ram and Sri combined with going to college and averaged out. Essentially at the end of the day, if you have a sentence like Ramsri is going to college, whichever word, in this case Ramsri, doesn't have a direct entry in the vocabulary of Word2vec algorithm or word vector algorithm, fast text will split the out of vocabulary word into its subword tokens, where each of the token will have entry in the fast text vocabulary, and we'll just take sum or averaging of that when we are considering the sentence vector of the whole sentence.